Hello everyone, I'm Tomasz Oltyński. Thank you for watching this talk and thank you organizers for giving me this opportunity to present our work on the 21 centimeter forest in the late end reionization models. I will start by briefly describing what the 21 centimeter forest is. Then I will move on to the Sherwood relic simulation suite used in this work, and I will finish by talking about different mechanisms affecting the observability of the 21 centimeter forest and what we might be able to learn in the forthcoming observations of this signal by SK and maybe LOFAR. So 21 centimeter forest, the idea behind it is very similar to the Lyman alpha forest in the sense that it's a signature of neutral hydrogen structures in the spectra of radio loud distant sources. 21 centimeter forest is complementary to the Lyman alpha forest because it is strongest in cold, dense, and neutral hydrogen. So this means that not only it can be used to probe the end of the epoch of reionization, but it can probe also the rest of the history of the reionization. So redshifts higher than 6, for example. It has been also proposed that it can be used to explore other things such as mini-halos or warm dark matter. One of the biggest challenges that the 21 centimeter forest observations face is the abundance of bright enough radio loud sources at such high redshifts, because we are not really sure how many there should be. However, in recent years, 4 radio loud quasars at redshift higher than 6 have been detected, so this is encouraging. We use Sherwood relic simulation suite in our work, which is a suite of cosmological simulations which use the hybrid hydrodynamics and radiative transfer approach. The boxes we use are 40 co-moving megaparsecs over H on the site. That means that we do not capture the largest H1 regions. On the other hand, this way we can achieve high mass resolution, which is important for the 21 centimeter forest studies because this observable tracks small-scale structure. In these simulations, we incorporate novel late-end reionization models in which the reionization finishes at redshift 5.3. These models are motivated by Lyman alpha observations, such as the clustering of the Lyman alpha emitters or large spatial fluctuations in the Lyman alpha opacity. Our model, as you can see here in this plot, agrees or is broadly consistent with measurements of the ionization fraction and Thomson scattering optical depth. And in this model, large islands of neutral hydrogen can be found at redshift as low as 6. As you can see here in this photoionization rate map, these dark spots are still neutral. So this means that there is a possibility that we might be able to detect 21 centimeter forests at such low redshifts. So let's see how different mechanisms affect this observable detectability of the 21 centimeter forest. Here we show the distribution of absorption features at redshift 6. In the black line is our fiducial model of patchy latent reionization model. In the fuchsia line, you see homogeneous simulation run. So these two models differ in the morphology of the reionization. However, their mean photoionization rates evolution is identical. So what we compare here basically is the effect of the hydrodynamic response, particularly pressure smoothing, of the gas to the patchiness of the reionization. And as you can see here, the patchiness enhances the signal slightly at high opacities. We also look at the redshift space distortions, how they affect the signal. So the black line is the identical to the previous slide. So that's our fiducial model. And the fuchsia line is the model in which we neglect peak-level velocities. We set them to 0. And as you can clearly see, the redshift space distortions boost the signal significantly at high optical depths, which is qualitatively consistent with studies such as SEMEL in 2016. We also look at the effect of X-ray background from the soft X-rays, which we parameterize with the FX parameter, which is the efficiency of the X-ray background following the approach used in Furlan 2006. The FX lower or equal to 10 is consistent with the measurements of Lyman alpha observations at redshift 6. FX larger or equal to 10 to the minus 3 is consistent with 21 centimeter power spectrum measurements at multiple redshifts. So we can see that the FX is still largely unconstrained. So let's look at our simulated 21 centimeter forest spectra here. So as we increase FX, the IGM experiences more heating from the X-rays, and therefore the signal is suppressed quite a lot. So this is consistent, qualitatively consistent with studies such as Meck and White 2012. So we can also see this behavior in the distribution of the absorption features here. So as we increase FX, so we go from the black line to the fuchsia one, you can see that the signal is suppressed quite a lot, even more than in the case of redshift space distortions. So given this strong sensitivity of the 21 centimeter forest on this parameter FX, let's see if we can use forthcoming observations of the 21 centimeter forest to constrain the FX. Imagine you observe one radio source with SK1 low with 1,000 hours of integrated time, and this one radio source will give you a spectrum of redshift path length of 0.2. Then this dashed line here tracks the maximum FX as a function of the threshold flux, which is the minimum transmitted flux at a given absorption feature. So the maximum FX that the IGM can experience, such that you expect on average at least one absorption feature of a given strength in this spectrum of one radio source. If you manage to observe 10 radio sources, you can track this solid line here. In other words, if you detect no absorption features of a given strength in the spectra of 1 or 10 radio sources, then what you can do is to disregard the parameter space below these lines, and hence you can put a lower limit on the FX. I should point out that this is model dependent constraint, and we included no instrumental features in our modeling except the spectral resolution of the telescope. So for example, if you detect no absorption features of 2% absorption or higher in the spectrum of one radio source, that means that you can put a lower limit on FX to be 0.017, and if you have no detection in 10 radio source spectra, then this increases to this limit increases to 0.032. To get some intuition of the what the brightness of the sources should be, we also show this S min, which is the minimum intrinsic flux density required to detect absorption feature of a given strength with signal to noise ratio of 5. We have done this calculation for LOFAR as well, and we find out that the constraints you can put on FX are weaker and the requirements for S min are higher. So to sum it up, we use Sherwood relic simulation suite, which incorporates latent reionisation models in which the reionisation finishes at redshift 5.3, And in this scenario, and in the case that the IGM is treated by soft X-rays background only modestly, strong 21 centimeter absorption features can be detected by SK and possibly by LOFAR. And we also showed that the null detection of the 21 centimeter absorbers with these telescopes should provide an interesting lower limit on the soft X-ray background, which should be stronger than the current constraints. So thank you very much for your attention.